All right, after reading it in my textbook a little more carefully, I think I have a deeper understanding of the derivation of Simpson's rule for approximation. So let's go ahead and work this out. Okay, so suppose we have a curve that looks, I don't know, suppose we have a curve that looks something like this, and we want to estimate the area under it. We've done rectangles, we've done trapezoids, now it's time to do parabolas. So what we want to do a little bit differently from the rectangle and trapezoid approaches is we want to cut this area up. Let's say I want to calculate the area of the region starting here, we'll call this x0, and ending over here. Let's say I want to calculate the area of this whole region over here. So what I want to do is cut up the area between these 2 points. I guess I would actually call this A equals x0, and I'll call this B equals, I don't even know, we'll just call it xn. So what we want to do differently is we want to cut it up into an even number of subintervals. What we want to do is cut this up into an even number of subintervals, and the reason for that will become apparent in a couple minutes. So let's see, I'm just going to split right down the middle, so somewhere around there, and then somewhere around here, somewhere around here. And yeah, how about we do a couple more splits? That should be enough. So let's see, I'm going to have an x1 and an x2 and an x3 and an x4 and an x5 and an x6. And I guess xn over here is going to be 8. So that's a total of 9 x's because x0 is our starting one. And yeah, so we've got 9 different points, which leads to 8 different subintervals. 0 to 1, 1 to 2, 2 to 3, 3 to 4, that's 4 of them. 4 to 5, 5 to 6, 6 to 7, and 7 to, I guess, 8 over here would be the other 4. So we have an even number of subintervals, and for each of these points I'm going to go ahead and name these f of x values as y1 and y2 and y3, or wait, no, that's y0, y1, y2. That'll be y3. That will be y4. y5. y6. y7. And y8 or yn. Okay, so now what I want to do is we're going to approximate the area under this curve by slicing it into a bunch of areas under parabolas. So if you've done the most basic of integrals, you already know that the area under a quadratic function suppose, for example, we are calculating this area over here, is going to involve cubing x and multiplying by a third, and there will probably be other factors depending on what exact parabola that you have. So we can basically split the area under this curve into these areas that themselves have at least some curvature above them, if nothing else. So one such region would be this over here. if I take these 3 points, I can come up with the equation of a parabola that fits them. I can come up with the equation of a parabola that fits them, and then I'll have some sort of approximate curve. Maybe it looks something like this, for example. As you can see, it's not exact. There's a little bit of underestimate over there, although maybe that's just because I drew it a little too low to begin with. But the point is, it's not going to be super exact, and that's okay. Again, it is an approximation method, but maybe a parabola is a better type of region to use than a rectangle or a trapezoid. Well, I think rectangles are the best, but at the very least, I think parabolas, or, well, I guess this isn't going to be a parabola so much as it's a region under a segment of a parabola. But the point is, using these curves to fit under other curves might be a more decent approximation than at least trapezoids. So I want to figure out what the area under this pink curve is. This pink curve doesn't fit exactly onto the blue curve, but should be a pretty decent approximation. So I want to figure out what the area under this curve is. So let's go ahead and try and get an equation for this curve. So this curve is going to have an equation of the form ax squared plus bx plus c. So for points x0, y0, x1, y1, and x2, y2 to fit this curve, I would have to satisfy the following conditions. I would have to satisfy y0 is equal to a x0 squared plus b x0 plus c, and y1 would have to satisfy a x1 squared plus b x1 plus c, and y2 would have to be a x2 squared plus b x2 plus c. Now I'm going to call the spacing between the x's, and I'm going to say that these are equally spaced, even though I guess this one looks a little bit wider than some of the others, but neglecting my bad drawing skills, let's say that all of these x's are evenly spaced, and instead of calling it delta x, because that's going to look ugly once we do some of the math we're about to do, let's call it something simpler like W for width, or yeah, let's call it W, for example. Let's call it W. And later on we can change it back into a delta x if we want. So we'll say W is equal to the delta x between different x's. And we can define delta x as just being, let's see, b minus a over n. b minus a over n, the full length of the interval divided by the number of subintervals that we cut it into. That works. Okay, so we have this. Let's leave this alone for a second, and let's go ahead and figure out the formula for the area under our curve. So there's a simplifying assumption in my textbook where they say, let x1 be equal to 0, and then they argue that you can get away with this because if basically imagine shifting this whole graph horizontally to the left until x1 is at x equals 0, and calculate the area and shift it back, because the area isn't going to change if you shift left and right. So we could get away with making that simplification. I'm not going to do that. I'm going to do it the hard way because I guess I like torture for some reason. I'm going to go ahead and do it the hard way and show that the hard way still gets us the same result that my textbook got doing it the easier way. So area of this region is going to be equal to, well, we know how to do this if it's a parabola. It's going to be the integral from, let's see, I'm going to have this centered at x1. And by the way, this is the reason why we want the number of subintervals to be even, so that we have 3 points and can always have like a central point among those 3 points. Also because we need 3 points to define a segment of a parabola. So anyway, I want to center this around x1, so I want x1 to kind of be like the focus of this. So I want to integrate from x0 to x2, which I'm going to think of as x1 minus w, to x1 plus w. Instead of x0 to x2, I'm calling them x0, I'm just calling it x1 minus w, and x2, I'm calling it x1 plus w. That's all I'm doing. So let's go ahead and write our function. It's going to be of the form ax squared plus bx plus c, and integrated with respect to x, and that'll be the area of that pink region. Okay, if I go ahead and do this integral, then I get 1/3 a x cubed plus 1/2 b x squared plus cx from x1 minus w to x1 plus w. If I go ahead and make that substitution, oh boy, here we go. 1/3 a times, for x cubed, I'm going to have x1 plus w cubed, x1 plus w cubed, minus x1 minus w all cubed, x1 minus w all cubed, plus 1/2 b, let's see, for x squared I'm going to have x1 plus w quantity squared minus x1 minus w quantity squared, plus c times x1 plus w minus x1 minus w, x1 plus w minus, in parentheses, x1 minus w. Okay, so there's going to be a bunch of terms that simplify from this. Let's see what they're going to be. So 1/3 a times x1 plus w quantity cubed is going to be x1 cubed plus 3x1 squared w plus 3x1 w squared plus w cubed minus, oh, and I should put brackets around all this, minus x1 minus w. If we cube that, then we get x1 cubed. Then it's going to be 3x1 squared times a negative w, so minus 3x1 squared w. And then next is going to be 3x1 times, if I square negative w, the negative disappears, so that's plus 3x1 w squared. And then if I cube negative w, I get minus w cubed. Close those parentheses and close that bracket. And then plus 1/2 b open a new bracket for this. Let's see, x1 plus w squared, so that's going to be x1 squared plus 2x1w plus w squared. And then minus, in another set of parentheses, the square of x1 minus w. So that's going to be x1 squared minus 2x1w plus w squared. Close that bracket. And then plus c times, let's see, we can already simplify what we have in here. x1 plus w minus, parentheses, x1 minus w. So the x1 minus x1 cancels out, and then w minus negative w, that's times 2w. Okay, and let's see what terms we can cross out from the a and b section of this. So x1 cubed minus x1 cubed is gone. The plus 3xw squared minus another plus 3x1w squared is gone. And that's it. Yeah, this is a positive minus a negative, and that's another positive minus a negative, so we're going to get some 2's there. And then what about the b section of this? So x1 squared and minus x1 squared, those are gone. And w squared minus another w squared, that's gone. Okay, so we end up with, I guess I'll write it over here, 1/3 a times 2 of 3x1 squared, so 6x1 squared. And also we have w cubed minus negative w cubed, so plus 2w cubed. And then plus 1/2 b times, let's see, 2x1 minus, or 2x1w minus negative 2x1w, so that's going to be 4x1w. And that's the b section, and then plus, I guess this will be rewritten as 2cw. And I forgot something, didn't I? Ah, it's 3x1 squared w. There needs to be a w over there, so that's, yeah, 1/3 a and then parentheses 6x1 squared w plus 2w cubed. Yeah, every term is going to have at least one w in it. So that's the next step, actually. I'm going to factor out a w, and I'm also going to factor out, I'm going to factor out a w from everything, and I'm also going to factor out a 1/3 from everything. So I'm going to factor out 1/3 w. So this equals w over 3 times we've got, I guess this will be 6a x1 squared plus 2a w squared. Yeah, the 1/3 is already factored out, and I took out a w, so just distribute the a onto what's left. Yeah, there we go. That's done. Plus, let's see, factor out a w and factor out a 1/3. Factoring out 1/3 is the same as multiplying by 3. So we've got a half and a 4, that's a 2, and multiplied by 3, that's a 6. So we're going to get 6b x1. And then over here, if I factor out a 1/3 w, the w is gone. from 2CW and multiply by 3, so that's going to be plus 6C. Did I do all my math right? I feel like I may have messed up a step somewhere here. Let me actually check my other... Where did I put it? Oh, I stuck it in a book. Where did I put the book? Oh, there's the book. Let me double check my previous solution and make sure that I'm still on track. Where did I even write it on this card? This is what happens when you try to write your solutions on random things that you find on your desk. Let's see, 6266. Yep, okay, it's the same thing that I got before. Okay, we're on the right track. We're on the right track. So now what I want to do is compare this to these y's, but I need to make an adjustment here. So everything here is written in terms of x1. So I want to try and do the same thing to these y's, rewrite them in terms of x1. Y1 is already written in terms of x1, so let's fix y0 and y2 over here. So y0 is going to be a times x0 squared is going to be x1 minus w squared plus bx0 again is going to be rewritten as x1 minus w plus a c, and then y1 can just be copied as is. I'll leave that for later. And then y2 is going to be a x1 plus w quantity squared plus b x1 plus w plus c. And if I expand each of those, what do I get? For y0, I get a x1 squared minus 2a x1w plus w squared, and then plus b x1 minus bw, and then plus c. And for y2, I get y2 is equal to a x1 squared plus 2a x1w plus w squared plus bx1 plus bw, and then plus c. That's cracking open all the parentheses and distributing the a and b. Oh, and I forgot, that's going to be a w squared, and that's going to be an a w squared as well. Not that it matters, because I believe these are going to cancel. Oh, no, they're not going to cancel out. Okay, let me write it in a different color so it's more visible. That's an a w squared there, and an a w squared over there as well. Okay, let me actually just rewrite all of the y's. I'm going to rewrite them anyway. Let me just rewrite all of my y's, y0, y1, and y2, neatly, and juxtapose them against this, and let's see what kinds of insights we can get. So I'm going to copy this over. So area equals W over 3 times, let's see, 6ax1 squared plus 2aw squared, 6ax1 squared plus 2aw squared plus 6bx1 plus 6c plus 6bx1 plus 6c. And then for the y's, I've got y0 equals, actually, I think I want to start with y2 since it has all the positives. So y2, ax1 squared, 2ax1w. So I'll write, I guess I'll write it over here, y2 equals ax1 squared plus 2ax1w plus aw squared, and then plus bx plus bw plus c. Okay, and then y1 I'll copy in a minute, and then y0 is going to be ax1 squared minus 2ax1w plus aw squared, and then plus bx minus bw plus c, and y1 is just, we left it untouched, ax1 squared, ax1 squared plus bx plus c. Okay, now if we compare this to the stuff in the brackets over here, you might notice something. Let's start by adding y0 and y2. What happens if I add y0 to y2? If I do y0 plus y2, and I'm writing y2 all the way out here for a reason. If I do y0 plus y2, these terms cancel out, and these terms cancel out, and I'm left with 2ax1 squared. I'm left with 2ax1 squared and 2aw squared and 2bx and 2bx, or bx1 rather. I forgot the ones. Why did I forget to write the ones? Yeah, there we go. That's better. Plus 2bx1, if I'm adding y0 and y2, and plus 2c. I wonder who is calling me. Give me a second. Okay, we can respond to that later. Okay, where were we? Right, we added y0 and y2. So now we have this. Well, look at this. We've got some of the stuff in the brackets now. Now we just have to add a little bit to it. So what are we missing? We've got our 2aw squared, so check. And we are missing 4 of ax1 squared and 4 of bx1 and 4 of c. Well, I've got ax1 squared plus bx1 plus c over here, so what if we take this and multiply it by 4 and add it to the mix? So if I add 4 of y1, if I add 4 of y1, so plus 4 times ax1 squared plus bx1 plus c, now we get a grand total of 6ax, whoops, that x is too small, it looks like a subscript, ax1 squared plus 2aw squared plus 6bx1 plus 6c. So now I can rewrite, now I can check off these as well. Now we've got everything. So I can rewrite my area. I can rewrite area as area equals W over 3 times y0 plus 4 y1 plus y2. And why on earth would we want to write it this way? Well, because now you don't have to deal with all of these terms. Why did I even point there? Now you don't have to deal with all of these terms. Now you don't have to, mix in your w's and your x's and remember all of these coefficients. You can just straight go to the curve that you have and plug in the y0, y1, y2, etc. If you are approximating the area under this function, call it f of x, then now all you have to do to calculate area is take the width per subinterval divided by 3 and just plug in f of x0 plus 4 times f of x1 plus 1 times f of x2. So area for at least a given pair of subintervals is going to be W. I guess we can now just call it delta x. I didn't want to call it delta x before because then we would have had a bunch of delta x's squared and cubed and whatnot, and having to write more parentheses around that would have just made it a lot uglier. So now we can call this f of x0 and 4 f of x1 and f of x2. Or more generally, we can say area for a given pair of subintervals is equal to delta x over 3 times 1 of f of x I minus 1 plus 4 f of x I plus 1 of f of x I plus 1. So the benefit is that you can just plug x's into the function you're trying to approximate and just plug in 3 numbers and you're done, rather than having to, integrate and do all of this algebra every single time. Now it's a simple problem of plug in numbers and make substitutions. Okay. There was, I think, something else I wanted to comment on here. What was it? Let me think. So that is the area for one sub-region, one pair of subintervals. The next pair would be from x2 to x4. The next pair would be from x4 to x6, and so on. So basically the x1 isn't going to repeat. So if I were to do the next region, x2 to x4, if I were to do this region next, what is its area going to be? Well, the area of that next region, so I guess I'll switch colors. Area of next region, what color have I not used yet? I don't know if I've used you. Have I? Yeah, I guess I have. Okay, I know which color to go with. Let's go with this one. So, I guess area 2, we'll call it, is going to be equal to the same delta x over 3, this time times f of x2 plus 4 f of x3 plus f of x4. Right, x2, x3, and x4 would be the 3 points to consider for the next region. So what we see, the pattern that develops, is that if we were to do all of these regions, all of these pairs of subintervals, then by the time we're done, we see that f of x2, we're going to add all of these areas. So here's area 1, here's area 2, and then for the total approximated area, we're just going to add all of those up. And what ends up happening is that the last f of x of the previous area is the first f of x of the next area. So these are going to double up, and you're going to have this sort of alternating pattern of 2, 4, 2, 4, 2, 4, except of course for the very first f of x and the very last one. So you get total area approximated by areas under parabolas is going to be delta x over 3 times f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus 2 f of x4, and so on and so forth until you reach the end where you get plus 4 f of x n minus 1, and then plus just 1 f of xn, where xn is your final x. So 1 at the beginning, 1 at the end, and then the pattern is 4, 2, 4, 2, 4, 2, 4, 2. And all that multiplied by delta x over 3, the delta x being, what was it? b minus a over n, or xn minus x0, if you will. Okay, so there you go. That's Simpson's rule explained and derived in a little bit more detail. I wish the book hadn't worded things in such a confusing way. I mean, I've seen worse in terms of textbooks. It wasn't too terrible once I actually slowed down and read it carefully, but still, I think my textbook could have done better at explaining it. And now I know more than I ever wanted to know about approximation, so I guess thank you to the student who asked me about this, and I hope I never have to do this again, but I get the feeling that I probably will. Anyway, hope you enjoyed. Take care. I'll see you in the next one.